Okay, so if the last few people could come down and find a seat, please. So today we're going to move on to talking about, okay, it's time to quieten down, please. So today we're going to talk about systems and feedbacks, which doesn't sound terribly exciting, I know, but it's one of the really important ways we have about how we address Earth system science issues and how we really start thinking and describing them, okay? But so I have thrown in a couple of fun examples at least, which should keep us a bit more excited as we go. And in particular, towards the end of the class, we're going to talk about this idea of Snowball Earth. And it's not a sort of a made-up thing. This is actually something that we think happened maybe sort of 700, 800 million years ago. The Earth became very nearly entirely covered by ice, and it really had quite profound implications for life at that time. So we'll try and get onto that as we move through. So I wanted to make a quick start because I have a few announcements at the beginning. Hopefully you all got this by email, which is that we're looking for a note taker for the class. So if you create beautifully crafted notes, then you can get volunteer hours, units, or pay for that. So if you're interested, please do contact the Disability Centre, and you can help out a couple of your fellow students. Okay, and you have this by email as well, or if you need this information, it'll be in the notes after class. Second thing, a few of you have noticed this already, but remember we're going to be filming the classes this quarter and posting them on YouTube. Okay, so if you haven't had a chance or haven't seen it yet, I created a EEE quiz, not for credit, but you need to go in and fill that in, please. It has a video waiver, which basically says that we're not going to pay you for starring in ESS 1, okay? I'm afraid. So please do that, and once we get up and going with the class, then those videos should be posted the next working day for you to review. So if you have to miss a class, you can catch up. Okay? And then lastly, thank you all so much, those of you who took the time to send me an introduction. I really enjoyed reading them all. People have been to some really exotic places. For a lot of you, here is the most exotic place you've been because you're from a number of different countries. And I think a few of you asked me questions or have made comments, and I'll try and get to you as soon as possible. It's just my inbox is a bit flooded, but thank you so much. I really enjoyed reading those, and I have a bit of a better idea now about actually who you all are, which is much nicer than anonymous faces. Then lastly, as someone very smart pointed out to me, my percentages didn't add up to 100 last week. Okay. So on the real syllabus on the website, it's all fine, but I just hadn't changed the slide from last year, which says that each of the midterms is worth 18 rather than 16%. Okay. So that's all of the boring announcements over with. So today we're going to talk again about what Earth system science is, because the first day is a bit of a brief introduction, and then we're really going to talk about ways of describing the Earth system. So what is this word system? Systems can be open or closed, so we're going to talk about that. We're going to talk about reservoirs, fluxes, and residence times. And then we're going to talk about feedbacks, both positive and negative feedbacks. And you're going to have a chance to work through a problem with your neighbours and construct a feedback process. And then lastly, we'll just touch on cycles very briefly, and we'll come back to those in a big way much later in the class. Okay. So, Earth system science. You are all in an Earth system science class. It's a good thing if you know what that is. It's the science that studies the whole Earth as a system of many interacting parts and focuses on the changes within and between those parts. And really that's the focus of the discussion groups this week. So I heard from Starrell that the people this morning had fun out in the park, identifying different components and thinking about how material and energy is being transferred between those. Because everyone always walks around with their phone and you never really think about it. Although I would say if you're out in the park and it's windy, don't stand under a tree too long because those branches tend to fall off quite often. Okay, so here are the 4 spheres that we talk about with a little bit of an extra one that we've added recently. So we have these 4 spheres that we use to describe the Earth system, and material moves between these different spheres, and we could call them reservoirs if we wanted to, at different rates. And if those rates change, then the size of the reservoir might change. And the reason that we have to view the Earth as a system like this is, I mean, for example, think of carbon. Carbon is our main problem right now. It's obviously the source of a lot of energy because we burn these hydrocarbons to generate energy. But then that carbon ends up in the atmosphere. It doesn't just stay in the atmosphere, though. A lot of it ends up dissolved in the oceans, which is gradually acidifying them. And it also gets taken up by plants, okay? So we can't just study the problem of carbon in the Earth system from one perspective. We have to really think about the whole Earth. So the atmosphere, I think I said this last week, but just to make sure you know, is that mixture of gases, the nitrogen, oxygen, argon, water vapor, things like that, that surround the Earth. The hydrosphere is all of the Earth's water, apart from water vapor, okay? So when I talk about the hydrosphere, I mean the oceans, which are by far the hugest reservoir of water on the Earth. And then we have things like the cryosphere. Just like cryogenics is to do with ice and cold, the cryosphere is ice. It's sea ice, it's glaciers, it's ice sheets, it's snow, anything like that. And then we also have the underground water, so groundwater, which is a big source of our water in California. Then we have the biosphere, which is all of us and all of the organisms around the world. The geosphere, that's the solid Earth, so rock, some components of soils, and that tends to be a bit slower to react, so it's something that on sort of decades or longer is not something we often think about, but is really, really important for how the Earth responds on longer time scales. And then we sometimes add this fifth sphere, which doesn't really fit in with any of these, but we call it the anthroposphere, and it's the parts made or modified by humans. And those groups that were out in the park today thinking about how much of Aldrich Park is actually a natural system and how much have we influenced it. We've obviously had a huge influence on the Earth in certain parts. Okay? So, let's think about systems, and specifically open versus closed systems. So, a system is just something that we arbitrarily define as a portion of the universe that we're interested in. Okay? And so I could say UCI is a system. And we have freshmen coming in and we have seniors coming out, okay? Or this classroom is a system. We have people coming in and out, we have material moving backwards and forwards. And so we can characterize this system on the basis of whether it exchanges energy and or mass. Okay, so we have three possibilities down at the bottom here. So an isolated system is one that doesn't exchange any energy across its boundary, and it also doesn't exchange any matter. Can you think of anything that behaves like that? No. It's a nice theoretical idea. It doesn't exist in reality, okay? So that's the nice thing. If I give you an exam question and I say, is this an open, closed, or isolated system, you can already cross one off the list, okay? Isolated systems don't exist in the real world. It's really impossible to stop that transfer of energy. Even things like vacuum flasks, eventually there's transfer of energy across that. So we're left with this idea of closed systems and open systems. And as you can see, we've got our little sort of tub of water there, and it's sort of made of glass or something like that. So it's sealed across the top. So even if that water in there evaporates, it can't get out. So we have no matter moving across those boundaries. Everything within that little sort of tub is sealed shut. No stuff, no matter, no so gases, no water vapor, anything like that is moving across that boundary. But what is coming in and out is energy. If we left that out in the full daylight outside, it might warm up inside, and that's because there's a transfer of energy in, and then there's an equivalent transfer of energy out. So that's our closed system, and then we have this open system idea, which is everything can be transferred across that boundary. So we definitely still have energy coming in and out, but now we can also exchange matter. So in this case, the baseball's gone in, water has gone out, we've exchanged matter across that boundary. Everyone clear on this idea? It's not too complicated, I don't think. So, prove to me it's not complicated. So think about the Earth. Is the Earth an open system, a closed system, or is it neither? Okay, has everyone had a chance to answer? No more frantic scrambling for iClickers? Okay, let's take a look and see what people thought. That's interesting. Okay, so an open system. What's exchanging from the Earth out to space? Energy is definitely transferring, but does that narrow it down to an open versus closed? Because in both cases, energy is being transferred across the boundary, right? So we want to think about matter. Are we gaining or losing matter from space? Do you want to change your answer? Yeah. So yes, this is why I gave you the neither opportunity. Okay, so we think of the Earth as a nearly closed system. So if you think about, I mean, space is a vacuum, more or less a vacuum, right? So we're not often adding more material to the Earth, and we're not really losing very much. Rocks don't float off out to space, okay? So there are a couple of exceptions, though, which my friend at the front pointed out, which is that every now and again, and last year quite spectacularly, or earlier this year quite spectacularly, we get little additions. So things like asteroids, comets, meteorites. So day to day it may not make a huge difference, but obviously over time it actually formed the Earth. Okay? Does anyone know what we're actually losing from the Earth? Yeah. Hydrogen, and the one up from that? What's slightly heavier than hydrogen? Helium. So all of your nice helium balloons, okay, we're actually a bit short of helium. It's one of the things that we're a little concerned about, because do you know how we get helium? No? People think we get it from the air. We don't actually. We mine it. Isn't that weird? So pockets of helium gas collect underground just like sort of natural gas, and we extract it, and that's a big source of our helium. The problem is right now is that once that helium is used in our nice balloons, or in medical equipment is another big user of helium, it floats off into the atmosphere, and eventually it's light enough that Earth's gravity doesn't retain it, and that hydrogen and helium are gradually escaping away to space. So make the most of your helium balloons right now, because it might get a bit pricey in the future as we start narrowing down. So it's much more important that our MRIs and things like that in hospitals work, unfortunately. So helium is an interesting one. So you're absolutely right that Earth is a nearly closed system, in that we really don't often transfer matter across the boundary. It's tiny amounts of matter that are getting transferred, but we do transfer a lot of energy, because where is our energy mostly coming from? The sun, absolutely. So it has to reach us, and it heats us up, and then in turn we radiate heat back out to space. And we're going to learn a lot more about that on Friday in particular. Okay, so energy comes in. So the sun is radiating radiating out to space, and the Earth intercepts a portion of that. Some of it gets reflected straight out. Some of it gets absorbed by the Earth's surface or the Earth's atmosphere. And then we, in turn, because we also have a temperature, radiate energy out to space. Okay. And then in terms of matter, what's coming in? Comets, asteroids every now and again, and out hydrogen and helium, which are gradually drifting off because they're so light. They're the lightest elements we have. Okay. So there are some pretty strong implications of us living on a closed system. And that is that our resources are finite. If we use up all our copper, we can't get any more on Earth. We'd have to go elsewhere in the solar system to get it, which is why these people come up with crazy ideas like asteroid mining, going out and capturing asteroids and mining them. And so this is one of the things we really need to think about as our population has really exploded in the past sort of 50, 100 years, is our resources are finite. They have to be shared out between everyone. And so the more of us there are, the less resources there are per person. We can't throw things away. There is no away for things to go to. And this is something that we're all a bit guilty of, because we put things in the trash and then we never really see where it goes. But obviously that all builds up. And that's another of the problems that we've had as our population have grown, is that we can't just get rid of stuff we don't want. And then the other thing that is a very strong implication of us living in a closed system is that changes in one part of that system therefore affect everything else. So the example I had earlier, which is carbon, if we're going to extract carbon from the geosphere in the form of fossil fuels, burn it, it doesn't just sort of disappear. That carbon is transferred into the atmosphere. Because it's a closed system, you can't get rid of it. It just cycles around within that system. Does that make sense? Good. So that's really thinking about open versus closed systems. Can you think of an example where humans have been exploring where we really do want a closed system for a few days at a time? Where have humans explored that has been somewhere different from sort of where the average of us would go? Sorry? Alaska? Yeah, well, that's pretty close. You'd want to be wrapped up warm, but still, we'd still be exchanging stuff. How about deep? Yeah. The deep sea. Okay, in a submarine, do you want it to be an open system exchanging with the exterior? No, definitely not. Okay, how about the other extreme? Where have we gone where you would also not want to be exchanging? Space, absolutely. So closed systems are really quite helpful, okay, for when we want to explore, but it's difficult to maintain those over longer periods. We need to resupply and things. The Earth's amazing, but it acts as this closed system and everything just keeps going. It's really cool. So let's have a think about how we look at really complex systems. So unlike sort of chemistry, sort of intro chemistry, we're not going to look at one thing and follow simple rules. We really have to think about these quite complex interactions going on. And so we did tend to sort of follow this set rule, which is, first of all, we have to identify the components of the system. And we have to be sensible about this, because if we're going to look at an ecosystem, we might not want to look at each individual species. We might want to lump things together. But initially, we want to identify the components and how they interact. And that's a bit of what you're getting a chance to do in the discussion section this week. And then we want to think about the residence time. So once we disturb something, how quickly does that change propagate through the system? And we'll have a chance to practice that in a second. And then we want to identify feedback loops. And feedback loops are hugely important for the Earth system. They can act both in a positive way. A positive feedback is not something that we want to happen. Okay? A positive feedback is not a positive outcome for the Earth in the way that we think of it. The way we define it is the positive feedback is something that amplifies a change. So for example, if the Earth got hotter and we got more water vapor in the air, which absorb more heat or something like that, then that temperature would increase further. So it's an amplifying change. It's a positive feedback. It may not be very good news for us, but it's still described as a positive feedback. And negative feedback is something which stabilizes the system. We take that system and we nudge it. We maybe make it a little bit warmer. Some other process happens to nudge it the other way and make it colder again. That's our negative feedback, and we'll have a go at those in the end. And so especially for things like the Earth system and things like the climate system, which we're all really interested in, you can imagine that we can't do this on paper. This is something that computer models have really helped us out with, because there's such different portions of the system. They're all interacting on different timescales. We really need those computers to help us, first of all, work out what might happen and also refine what we know about the system. Okay, so let's define some terms very quickly. Our reservoir is not just a lake, okay? It's the amount of material of interest in a given form. So, for example, our atmosphere acts as a reservoir of carbon. The biosphere acts as a reservoir of carbon. A flux is when material is added to or taken away from that reservoir. And if we're adding, that's called a source. And if we're removing material from a reservoir, that flux is called a sink. If we say something is in steady state, we mean that what's going in is equal to what's coming out. So, for example, if I turned on the taps in my bathtub, then I also opened up the drain, then as long as the inputs from the tap equaled what was leaving from the drain, the level of the water would stay the same. It would be in steady state. And then lastly is this residence time. So you'll get to do math for the first time. I know how excited you all are about that. And it's really just the time that it would take to empty or fill the reservoir. That's the easiest way of thinking about it. But actually, it's a measure of the amount of time the average little molecule would spend in that reservoir. So in my example where I said that the bathtub is full, I open up the taps and the drain is also going, so the level stays the same. Are the individual molecules of water going to be the same? No, because they're being added and they're being taken away. So the molecules are changing, even if the absolute size of the reservoir isn't. And it's the same thing for oceans, it's the same thing for big ice sheets. They may be staying the same size, but the water molecules are moving in and out of them. And so the amount of time, the average amount of time that one molecule would stay in that reservoir is what we call the residence time. So, really complicated maths, you can tell. But my bathtub holds 30 litres of water. Water from the taps flows in at 5 litres per minute. Water drains out at 5 litres per minute. So what is the average residence time of a water molecule in my bathtub? And so you can see the formula there. Notice the or, total sinks or total sources, okay? And tell me, how long would a little molecule of water stick around? A few more seconds just to collect the last few votes. Okay, so let's take a look. C, 6 minutes, yes, 70% of people were right, congratulations. First math down. Okay, so what's my reservoir in this example? The bathtub, and how much is in it? 30 litres, so the amount inside the reservoir is 30 litres. What's the source in this case? Yep, 5 litres per minute from the taps. What would be the sink? 5 litres per minute. So you only need one of those, remember. It's either the total sinks or the total sources. And so 30 divided by 5 is 6, so hopefully everyone can do that part. Okay, so that's all very well, but it's a bathtub. It's not particularly exciting, so let's think about something that's perhaps more the real world. Okay, the Salton Sea. Who's been to the Salton Sea? 1, 2, 3, 4, 5. Okay, the other people haven't gone because, to be honest, it's not that wonderful a place. You would agree? Yes. Okay, and it used to be a very exciting place to be. In the 60s, they built resorts around it. It was going to be the Riviera of California, and people went there. But the problem is that, is the Salton Sea natural? No. How did it get created? Does anyone know this? The people who took my class last quarter know. We did it by accident. Okay, earlier on in the 1900s, we tried to create an irrigation system using water from the Columbia River, and it went a bit wrong, and we actually diverted the whole Columbia River into the desert for a couple of years. Okay, and it built up this enormous Salton Sea, and there have been lakes there before in the past, naturally, but it shouldn't necessarily be there today. And the problem is that that water is no longer coming in. We're losing a lot more water than we are gaining it, and so it's gradually drying up. And as it does that, it gets saltier and saltier, and there are some other environmental issues also associated with this. Okay, and there's a really cool little 3 or 4 minute video up there, so hopefully if you're interested in this, you'll have a chance to watch it and see what's going on. So first of all, we have to identify the components of the system. So what is my reservoir? The Salton Sea, absolutely. Okay, so my reservoir is the Salton Sea, and it contains about 9 cubic kilometers of water. What's going to be my source into the Salton Sea? Yep, right now, rather than in the past. Yeah, agricultural runoff. So we have a lot of fields and farmland around there, and we irrigate those farms. We also get a small amount of precipitation, not a huge amount, but it does collect in that basin, and so those are our sources. What about our sink? Where are we losing water from? Evaporation, absolutely. So this isn't a hugely complicated system. We have about 1.5 cubic kilometers per year going in from agricultural runoff, rainfall collection, things like that. And we have about 1.5 cubic kilometers leaving. And I've simplified this a bit to make the numbers match. Okay. So, is this system in steady state? What's happening to the level of the water? In my example, not in real life. Okay, last couple of seconds. Excellent, even better, 80% got it right this time, absolutely, which is we're adding the same amount of water each year that we're losing. And so the level of the lake is not going to be changing, it's in steady state. Okay? However, in reality, we aren't actually adding that amount of water in, and actually in the future, probably around 2018, unless our current policies change, we're actually going to be diverting a lot of the water that currently goes into that lake and sending it to San Diego and to other places for agriculture or just for human consumption. And so what we're interested in is, well, how quickly will this lake theoretically change? How quickly might it dry up? Because one of the problems that we have is because of all that agriculture, a lot of the things in pesticides, a lot of the things in fertilizers have run into that lake and have started collecting in the sediment at the bottom. And now as that lake dries up, so I'm thinking of things like arsenic, pretty heavy metals, things that aren't very good for us as humans. So as that lake starts drying up and exposing a lot of the sediment that was on the bed of the lake, then when we get strong winds, then that dust can get picked up and carried actually out to South California. And this is potentially quite a big health hazard that could affect all of us in South California in the next sort of 20 years or so if we don't find a way of trying to address what's going on with the Salton Sea. And so it's going to cost us billions of dollars to maintain. It would cost us billions of dollars not to. And so what do we do in that case? And there's some really interesting things being done at the university, thinking about water chemistry and the engineering and how we could try and stop some of these somewhat disastrous consequences of the lake drying up. So let's think about the residence time. Theoretically, our really simple model, how quickly could the lake dry up? How quickly do things happen? So, second example of the day. Again, what is the residence time of the average molecule in the Salton Sea? testing your mental math. Okay, last couple of seconds. Okay, 80% again. Okay, we've got it. So, the amount in our reservoir this time is 9 kilometers cubed. Our total sources is that inflow, which is 1.5, or you could do it with the total sinks, which is 1.5. So 9 divided by 1.5 is 6 years. So it actually is a very quick response time or residence time. And so this is why we're concerned, is that if we do divert all of that water away, the sheer amount of evaporation happening could really have quite a large impact very, very rapidly on the Salton Sea. So how good is our little prediction? So this is taken from a report which is about 30 pages, so if people get really, really excited about this, you can read that as well. It was done by the Pacific Institute. And it's quite complicated. The grey line there shows the level of the lake, and you can see the elevation on the left-hand side there. So we're already below sea level. We're already sort of 228 feet or something below sea level. But you can see that, say from 2018, which is about where this sort of orangey pink bar is, from that point onwards, if all of that water gets diverted away to San Diego or other places, you can see how quickly that lake level drops. It drops by maybe nearly 30 feet in just maybe a decade or so. And so it really does respond very rapidly. You can see that unlike our example, it actually finds a new level. It doesn't actually dry out completely. And this is because of feedback processes, which is the next thing we're going to talk about. Do you think the amount of evaporation happening from the lake will stay the same as it shrinks? No, absolutely. Because as we get less water and less surface area, there's going to be less evaporation. And so you find a new balance. So it matches the new inflow from rainfall or whatever else it gets. So it doesn't dry out completely necessarily. It's a little stabilizing feedback process that kicks in, and it finds a new steady state position. Okay, so it's an interesting problem, and no doubt you will hear more about it. So feedback loops, everyone's favorite thing, and they seem complicated at first, but I promise you they're not, and we're going to have a lot of chance to practice this over the quarter because they are so important. So this is what I was saying earlier, but I just want to stress it again. A positive feedback is not something that we want necessarily for the Earth. It's not a positive outcome. Okay? A positive feedback is that amplifying process. It's taking an initial change and making it more extreme. So in reality, it's usually destabilizing. It usually makes a problem worse rather than better. Okay? A negative feedback is damping or stabilizing. So we see an initial change and some other part of the Earth system kicks in and nudges us back the other way, and so we tend to stay where we are. Okay. So let's think of an example. So here's an example of a negative stabilizing feedback process that those of us with air conditioning really appreciated in August in particular when it got so hot. And I want to introduce you to some notation that we use, which is we create our little sort of boxes with the different components that can change, and then we draw arrows between them to show causation. Okay? And if an increase in one box is causing an increase in the other box, we draw a normal arrow. If an increase in the initial box causes a decrease in the next box, then we use one of those arrows with a funny circle at the end. Okay? So, if I increase my apartment temperature, what is going to happen to the amount of air conditioning used? Increase, yes, don't worry, I'm not trying to trick you. Okay, so what type of arrow would I use to connect these two boxes in this first case? The normal one, yeah? Because an increase in my apartment temperature is leading to an increase in the amount of air conditioning, and so we see a normal arrow, a nice one with a point on the end. Okay. If I increase the amount of air conditioning I use, what happens to the apartment temperature? It decreases. Okay, so what sort of arrow will I have going from the right-hand box to the left-hand box? An arrow with a circle. Okay, because in this case, that increase is leading to a decrease, and so I draw the negative part there. Does that make sense so far? I don't want to lose anyone at this point. No? Shall I do it again? Right, okay, good. I'm glad someone's brave enough to say. Okay, so my initial change, if I just take one part of the system, I say I'm going to increase the apartment temperature. Maybe the sun rises, comes in through the window. The temperature goes up, and so theoretically, if your system is working properly, the amount of air conditioning should go up as well. Okay? And because we're seeing an increase causing an increase, it's going to be a positive coupling. Okay? An increase leading to an increase. And so that's the arrow that we draw between those two. But we can do the reverse now, which is that the amount of air conditioning we use in turn will cause a decrease in the apartment temperature. So in this case, an increase is leading to a decrease. And in this case, we use the second type of arrow with the circle on the end. So an increase leading to a decrease, which is a negative coupling. So overall, I've told you at the top, this is a negative or a stabilizing feedback. If you follow that loop around, and they always have to be loops, remember? So it's a feedback loop, okay? So you can see that as I follow those arrows around, it forms a complete loop, and my initial change, if I follow that loop around, is stabilized, okay? Takes that initial increase, and the loop will try and decrease it back to what it was before, okay? This is a negative or stabilizing feedback. So, I want to challenge you a little bit. I want you to help me with a positive or amplifying feedback. So again, just think of the same process again. And in particular, this is one that is really important today, and important if we're going to talk about the Snowball Earth. And so we have this interaction between incoming sunlight, the amount of ice, and the temperature of the Earth. So if you imagine that the whole of the Earth was covered with a black surface, if we asphalted everything, okay, you can imagine that a lot of the incoming sunlight, a lot more of it would be absorbed, and so the Earth would be warmer. If instead we have ice sheets covering the northern hemisphere or something like that, that nice white surface is reflective, so that incoming radiation, a lot more of it is reflected straight back to space without actually going into warming up the Earth. Okay? And so I've started you off, I've drawn you out the boxes. So I want you to think about what would happen if I increase the amount of sunlight reflected back to space. What would that do in turn to the temperature of the planet? What would that do to the amount of ice? And what would that do in turn to the amount of sunlight reflected back to space again? So work with the people around you and see if you can draw the right arrows between them. And I'll give you 2 minutes, and then we're going to come back and see what you got. So what do you think, Tina? If I increase the amount of sunlight reflected, what do you think I do to the temperature of the planet? Do I? If I reflect more sunlight rather than absorbing it?
It's the same. If it's reflected, but if it's covered in asphalt, then it warms.
That's right. So if I increase the amount of white area, it'll actually get cooler, right? Because we're going to be reflecting more away. So if I increase the amount of sunlight reflected, we're actually going to cool down the Earth a little bit. If we're going to cool down the Earth, what might happen to how much ice we have?
It will melt.
Will it? If it gets colder, are we going to have more ice or less ice?
More.
More ice, yep, okay. And if we have more ice, are we going to reflect more or absorb more? We're going to reflect more, yes, okay, got it. Yes, so it's one of those, it's a positive loop. So if we start off with an increase, it leads to an increase and increase. So it just goes into this death spiral, okay? And that's what happened to create the snowball Earth. So yeah, we'll see. Okay, got it? Great. Okay, so lots of conversation. That's either a good thing or a bad thing. So if I increase the amount of sunlight reflected away, so less is absorbed, more is reflected, what do I do to the temperature of the planet? Okay, there seem to be a lot of different answers being shouted at me there. So if I'm reflecting more, absorbing less, am I going to warm up the Earth or cool down the Earth? Cool down the Earth, excellent. Okay, great. If I'm cooling down the Earth, are we going to have more ice or less ice? More ice, okay. If I have more ice, am I going to increase the amount of sunlight reflected or decrease? Increase, okay. So what type of feedback is this? It's a positive feedback. So that initial increase in the amount of sunlight reflected goes back and increases it again. And so it's one of those amplifying feedbacks. We just keep going round and round and round, and we end up in this sort of death spiral of getting colder and colder and colder, right? So hopefully your arrows look something like this. Okay? So you have that negative coupling between the top two. The negative coupling with a decrease in the temperature of the planet will increase the amount of ice. And then lastly, we have a positive coupling from the increase in the amount of ice leading to an increase in the sunlight reflected. Okay, and this is actually what happened. Okay, so this is our snowball Earth hypothesis. And this is the idea that actually, at certain points in Earth's history, this has happened. So in particular, there are a few, it's difficult because it's such a long time ago, the geological record is a bit patchy. But if we go back, say, 750 million years or so, there's a series of these very long-lived glaciations, and we found evidence of glaciers almost all the way to the equator. And so this was the really interesting thing, and people couldn't quite explain it. But the more and more evidence we have, the more it seems that the Earth really did nearly completely freeze over. So temperatures at the equator were probably similar to what we get on Antarctica today. Does that sound like a very friendly place for life to exist? No. And this is actually a really interesting time in terms of the evolution of life as well, because it's right around the time when we start moving from single-cell, pretty simple creatures into this sort of multicellular world that we live in today. And this argument is that, well, maybe this sort of rapid switch between these sort of really, really cold periods and then subsequently much warmer periods perhaps drove some of this or gave evolution an extra kick in this sense. Because if we have this really positive feedback, which is amplifying, we're a solid ball of ice, why aren't we still today, oh bother, I just gave you the answer. Okay, why aren't we still today a frozen ball of ice? So who was quick enough to read it? What saved us? Volcanoes, okay, because what are we concerned about warming up the planet today? Carbon dioxide in our atmosphere is what we're concerned about warming us up today, because it can trap extra heat at the Earth's surface. And so if we think about what can happen, I mean, if we're not having a lot of life taking in carbon, then as we have more and more volcanic eruptions which release carbon dioxide into Earth's atmosphere, if that carbon dioxide is just collecting in the atmosphere above the Earth, then sooner or later we hit this critical point where that ice actually starts to melt away again. Okay? And so people were thinking it's maybe 13% of the atmosphere at that point was enough to get it to start melting away again. And of course, once it starts melting away again, we increase the temperature of the planet, we decrease the amount of ice, we decrease the amount of sunlight reflected, and so we actually go through that positive amplifying loop in reverse, and we end up with pretty greenhouse conditions for a while. And so this is really interesting time in Earth's history, which I just think is fascinating. So CO2 saved us there. So lastly, cycles. So if we think about Earth being a closed system and material moving between it, between different reservoirs, then really it's remarkable how stable, with a couple of exceptions that we just looked at, it's remarkable how stable Earth has been throughout its history. And this is because that movement of material and energy between different reservoirs often forms cycles. Things like the hydrologic cycle that you learned at school. We have the energy cycle, we have the carbon cycle, the nitrogen cycle. And lots of these are stabilized by negative feedback. So these cycles often involve lots of different negative feedbacks, which help to keep us in this sort of nice sort of steady state or equilibrium conditions. But now, of course, we've been changing many of these cycles, and so what we need to know is really where our new steady state is going to be. Just like with the Salton Sea, it will find a new steady state. The Earth is going to have to find a new steady state when our changes stop, and where is that going to be? It's one of the really interesting questions. So those are the cycles that we're going to touch on later in the class. I'm not going to go over them now. So there's a review for this week. I'm not going to read it through. But on Wednesday, we're going to think about whether there's life on other planets or elsewhere in the solar system. So please do the reading before you come. Okay, thank you.